Okay, very good morning. Hope you had a nice holiday. The weather, if you look at the weather really, sometimes I feel that it is the classic case of intention being there but implementation being zero. It's intending to rain for the last 2 or 3 days, but implementation is zero, no rain. So hopefully its implementation will be full today. What's your forecast? Did you check up the forecast? Already started drizzling, some implementation. But did you look up, do you look up the forecast anytime? Sorry? No, at least in the morning do you look up the forecast or no? At least for the sake of being in time series analysis, you should get used to looking at forecasts. And generally you can say if it rains then you reverse the prediction, and that is how you work with the practical forecast. Okay, good. So, let us get started. So, today what we are going to look at is exclusively auto-regressive processes. We discussed quite at length the moving average process. Now, if you recall, the moving average process takes birth from the linear random process when we assume a certain kind of structure for the impulse response coefficients, which is that the impulse response dies off after some finite lags. And we introduce that assumption primarily to handle the fact that there are an infinite number of unknowns to be estimated. But obviously that is not the only way. We can take another approach where we assume that the impulse response does not go down to 0 after finite time instants, but decays exponentially. Okay. Of course, that assumption alone does not help me address the problem, because still I have infinite number of unknowns to estimate. But before we go further, why is it that we are assuming that h of n decays exponentially? Why are we assuming that the impulse response should decay exponentially? What is the reason? Okay, where is the question of stationarity? Okay, but is there anything in the definition of the linear random process that is forcing us to make this assumption? Convergence of what? Go back to the definition of linear random process in your books and see what is it that we have stated clearly. What have we assumed on the impulse response coefficients? Absolute convergence, right? We have assumed that the impulse response coefficients, not only assumed, in fact we have required this to be holding, because we said only when this is satisfied I can assume that the series converges in a very strong sense, almost sure convergence. And secondly, this also implies that the variance is finite and the autocovariance also is absolutely summable and so on. So, there are several nice consequences of this requirement, and essentially amounting to convergence and stationarity, and therefore we have to necessarily assume that the impulse response decays exponentially. But as I said a few minutes ago, this alone does not satisfy the or actually solve our problem of this infinite number of unknowns. We have to make another assumption, and that assumption should allow us to go from infinite unknowns problem to a finite unknowns problem. That is the idea. Earlier in the moving average case, we resolved that issue by simply truncating the series, and we justified that by saying yes, there are many processes that satisfy that. In fact, if you take many real life processes, the ACF does support that assumption. So, it was not a very unrealistic one. Nevertheless, there are many other class of processes that do not really lend themselves to that assumption of finite impulse response coefficients. As you have seen in many of the real series, the ACF kind of decays exponentially, right, which means that the impulse response is also not really dying down after finite lags. And that is the reason we are pursuing this second approach. So, now the problem is of converting this infinite unknowns problem to a finite unknown problem by what we by an approach known as parameterization. That is, now we assume, for example, h of n, as you see on the slide, is for example alpha 1 lambda 1 raised to k, where alpha 1 is some real number and lambda 1 is such that it is less than 1 in magnitude. Why are we requiring that lambda 1 be less than 1 in magnitude? Because the impulse response coefficients have to decay, otherwise there is no guarantee. Remember that we have already said that IR coefficient should decay. Now, why are we doing this? Why have we assumed that H to be of this form? Can it be of some other form? As long as it decays, it is okay, that is fine. But are there multiple ways of decaying? Yes, it is possible. This is not the only way that H of n can decay, it can decay in a complicated manner too. This is one of the simplest forms of decay, known as the exponential decay, right. Exponential does not mean always e to the power of something, some kind of power law you can say, right. Now, did some angel come and tell me that this is how it should decay? No, I am just assuming it for mathematical convenience. Why is it mathematically convenient? We will see shortly, alright. But the most important thing that we should observe is by assuming this power law, this kind of an exponential decay, we have done something. We have actually converted a problem that was unsolvable to a solvable one. How? So, only two unknowns I have to estimate, alpha 1 and lambda 1, that is it, right. But this is a standard technique, it is not something new. We have seen this in high school, you know, even in our plus 1 plus 2 exam syllabus we have seen maths, parameterization of curves. See, you have to look at it this way, I have some sequence h of n that decays, okay. So, let us say n equals 0, anyway we have fixed it to 1, and then we it could increase, for example it could be greater than 1 at h at 1 and maybe even greater than 1 subsequently, but gradually it should decay, that is the requirement, and this is required for stationarity, right. In the MA model we have assumed that here after some m it is 0 thereafter. But now we are saying no, it need not be 0, it can go to 0 only asymptotically, but then there are infinite unknowns. However, now I solve that problem by assuming that there is a thread that is connecting all those dots, all those points, and instead of trying to estimate every point on that curve or the thread, I am going to assume a certain equation which we actually call as a parameterization. And why should it be of this form? What is the meaning of assuming this is what we are going to study now, okay. What tells me that h of n should have this form? It could be, for example, the second one that you see on the slide, it could be sum of two exponentials, alpha 1 times lambda 1 raised to k plus alpha 2 times lambda 2 raised to k. Nothing stops you from assuming that. Can I know upfront that such a power law is binding the impulse response coefficients for a given series? Yes, I can. But first let us understand now what is the consequence of this parameterization on the ACF, because ultimately we will always turn to ACF to tell us something about the series, that holds a key, right. So, now what we shall do is we shall take this parameterization for the impulse response, we will solve it for the simple case, that is we will begin by assuming that h only varies this way and see what form the linear random process equation takes. You must have guessed what form it takes, but let us see how what happens, right. So, let us now look at actually this case and write the equations for the linear random process at two different instants, okay. at k and at k minus 1. And the equations are shown on the screen, fairly straightforward, there is nothing magical about it. All I have done is I have substituted in place of h of n, I have substituted alpha 1 times lambda 1 raised to n. Now, the reason for writing v, that is this equation itself at two successive instants in time, is what? You must have, I mean, we have looked at this kind of situation early on, even in geometric series, when you are looking at a geometric sum of a geometric series, we use this trick, right, to calculate the sum of the geometric series. More or less it is the same thing. So, when we algebraically manipulate these two equations and write, we end up with this nice first order difference equation. Okay. So, that is the main point here. Do you see how that difference equation is born? It is very straightforward. Okay, there is a simple algebra there. So, Vk minus lambda 1 Vk minus 1 is alpha 1 Ek. So, look at how this simple parameterization has allowed us to convert first of all an unknown infinite number of unknown problem to finite unknown problem, and we have changed the shape of the equation itself. We have converted that convolution equation to a difference equation form, right. What is the advantage of a difference equation form? Plenty, there are number of advantages. One, of course, is it is easy to interpret. Now, one of the interpretations that immediately falls out as a consequence of this assumption is that by assuming this kind of a parameterization, what I am implying is that the process is dependent on its immediate past. It evolves as a function of its immediate past. So, I may make this mathematical statement, yes, behind every assumption there is an implication, and this is the first implication of this assumption that we are making on H. Whenever I parameterize H this way, I will whether I state it explicitly or not, I am implying that the process is evolving according to a first order difference equation. Whether you state it or not, that is a fact, and this mapping is unique in the sense that instead of assuming now this parameterization, I might as well postulate a first order difference equation model. If I were to solve the first order difference equation for the impulse response, what would I get as a solution for the impulse response? Again I will recover the same thing, alpha 1 times lambda 1 raised to n, of course assuming 0 initial conditions. Okay. Asymptotically, at least I will end up with that kind of an impulse response. So, that is the point here, whether you assume parameterization of that form or you assume a first order difference equation, the meaning is the same. In the literature of time series analysis, you will actually see the journey starting from the postulation of difference equation form, but unfortunately it is not so enlightening. Why somebody would define linear random process in a convolution form and suddenly think of a difference equation form is not clear. Of course, history tells us a few more things, that people did not come up with a linear random process in the first place. The Wiener school of approach assumed an auto-regressive form like the difference equation form as a starting point, whereas Kolmogorov's school of thought started off with the moving average thing, and then they both converged when they asked a question, when are these representations possible, then they collided at one point, which is the point of the definition of linear random process. So, we have taken that as a starting point. In certain textbooks, in fact in a lot of textbooks that are widely available, the linear random process is not necessarily the starting point, but I would like to present it that way so that you see the unification right up front, and then see the moving average and auto-regressive as children of those forms, and that how they evolve under some special circumstances. We need not always present any subject, and this is true not only for teaching but for research also, that the chronology of presentation need not coincide with the chronology of discovery. Suppose I am cooking a nice dish, right, and I have discovered how to make this very nice dish. I might have gone back and forth in terms of iterating, I must have forgotten coriander, chilies or whatever, ran to the shop. That does not form the part of the recipe. Run to the shop, get coriander. Have you seen anywhere in the recipe? Forget deliberately some spices. There is nothing like that, right? Discover accidentally after burning your tongue. Nothing like this is a part of the recipe. How is the recipe presented? As if it was discovered in the mother's womb itself. Take this many, these are the grains, this much salt, this much pepper and so on. As if Kekule discovered benzene structure in his dream. Kekule apparently had discovered the structure of benzene in his dream, right? Now you can't go into his dreams now and verify, but let us assume it's true. So these things did not come out of dreams. Therefore, do not get confused when a presentation in your course is different from what you see in the literature in terms of the chronology of discovery. The most important thing is, after discovering all the results, it's very useful and also important to put things in perspective and then put in order and say, I wish this was a starting point, right? So that future generations do not have to go through the same ordeal that the person who discovered this had to go through. You spare people of those ordeals. Likewise here, if you look at the time series literature, you will see people independently proposing auto-regressive models, moving average models, and then somewhere linear random process is born, the definition is born and so on. We will keep all of that aside. We will learn as if the linear random process was the starting point and see moving average and auto-regressive as special cases, right. So, this kind of perspectives need not exist in all books. It is just a matter of how much time you have spent and how much you have reflected on the topic. Anyway, so coming back to the point, the auto-regressive model, whenever you assume, now you should understand at the back of your mind, behind the scenes, what you are actually implying is that the impulse response coefficients decay exponentially. And we will discover something more as we go along, right. Any questions until this point? Okay. So, now we have already assumed that lambda 1 is less than 1 for stationarity. So, we know that this difference equation form is guaranteed to give me, I have not made any additional assumptions, right, in deriving this difference equation form. It is just an algebraic manipulation. So, I am guaranteed that this difference equation form will give me a stationary Vk so long as lambda 1 is less than 1 in magnitude, something that we have seen earlier also, right. So, we replace now, to bring everything into the notation that we have been using, we replace lambda 1 by minus d1, or you can say minus lambda 1 by d1, and absorb the alpha 1 into Ek, right. I do not have to assume alpha 1 as a separate thing. In fact, if you see this kind of a decay here, I have not mentioned, but we are assuming this kind of a decay for sorry, should have corrected me, n is a dummy variable. So, n greater than or equal to 0, anyway we have assumed h of 0 to be 1, correct. So, what will happen at n equals 0? Alpha 1 has to be 1. So, by absorbing alpha 1 into Ek, we are essentially saying set alpha 1 equals 1, and we have already gone through the explanation and arguments as to why we choose h of 0 to be 1. In other words, now instead of 2 parameters, we have only 1 parameter. That is how it appears to be. However, there are 2 unknowns. What are the 2 unknowns? Sigma square E. So, there is no escape, okay. It just manifests in a different form. That is something that you will see routinely in data analysis. There is no escape to things, whatever were the number of unknowns at the beginning, unless you have pumped in some prior information, the number of unknowns does not change, okay. So, this is your first order auto-regressive model. The name for regression is auto-regression is fairly straightforward. The series regresses onto itself, and regression is a term that is more widely used in hypnotherapy and so on, where people are regressed into the past to resolve some problems that have been troubling them and so on. So, it is more of a term borrowed from sciences. All right. So, the auto-regressive model has to be understood carefully. It says that the process evolves as a function of its immediate past, but that does not mean that there is no connection with its further past. It is, but that is more of an indirect or a propagated effect. Directly this AR1 model is dependent only on its past. What is a prediction viewpoint, and that will set the interpretation of an autoregressive model very clearly. From a prediction viewpoint, the AR1 model says, so long as you give me Vk minus 1, I can make the best forecast. I do not need Vk minus 2 or Vk minus 3 and so on, I just need the immediate past. Okay. In other words, any prediction for an AR1 process, any prediction of k of V at k given k minus 1, k, let me explicitly write here Vk minus 1, Vk minus 2 and so on, given the infinite past, is the same as just relying on the immediate past. Just Vk minus 1 alone is sufficient, the rest is not needed at all. This is completely contrasting to the MA model. If you recall, when we wrote the prediction equation for MA model, we had to recover Ek, and we said, oh boy, theoretically recovering Ek requires infinite past, right. So, in essence an MA1 model is an autoregressive model that actually requires infinite past, and we have talked about this equivalence also, and we will talk about it a bit later also. So, the AR1 model is such that the conditional expectation of Vk given the infinite past is the same as a conditional expectation given k minus 1. In fact, many a times this is called a Markov process, but I do not want to scare people, I am myself scared of that term. So, I will not use Markov process here, but there is a huge literature on Markov processes. An AR1 process is more or less a Markov process, that is how the Markov process is defined as. Now, you can extend this definition of an AR1 process to an ARP process, right. Straight away you can extend this definition, but let us look at this from a parameterization viewpoint. What is what would be the parameterization of the impulse response for an ARP process? How would you modify this parameterization? What kind of parameterization will lead to ARP? Sum of exponentials, very straightforward, right. So, you can say here instead of alpha 1 lambda 1 raised to n, sorry, you would say lambda I, alpha I lambda I raised to n. And still, you know, here of course how many, if you are looking at a ARP model, you are looking at p terms here, right. So, now instead of estimating h, we estimate the alphas and lambdas, that is the point. And here we assume that each lambda I is less than 1 in magnitude in order to meet this requirement here, the absolute convergence of the impulse response coefficients. Clear? Cool. So, obviously you can see that in the AR1 case lambda 1 is nothing but the root of the characteristic equation. So, now you can expect for ARP the lambdas to be the roots of the p roots of the characteristic equation, right, and we know what the characteristic equation. And again I would like to say this, that the mapping between the parameterization and the difference equation form is unique. So, if you assume a particular parameterization, you are implying a difference equation form of that order and vice versa. Okay. So, as we just mentioned here on the board, as we wrote on the board, a parameterization of the sum of exponentials form amounts to writing an ARP model. Again, as I said earlier, you will not find this, in fact I am not found this in any of the time series texts as a connection between the AR form and the parameterization of the impulse response form. It is purely presented as an autoregressive form, but this parameterization allows us to view the autoregressive model as a child of the convolution model that we have written. Okay. And of course, the consequence is that the stationarity requirements are now different. With the MA model it was pretty obvious, in the sense the stationarity was not an issue at all, just apart from the boundedness of the impulse response coefficients, but invertibility was an issue because we had to guarantee stable forecasts. On the other hand, in autoregressive models, stationarity has to be guaranteed. That means not all difference equation forms of the form that you see on the screen are necessarily going to give rise to stationary VK. We have deviated from the linear random process model, right. So, now we have to give a fresh set of constraints, restrictions on the coefficients, and those constraints are that the roots of the characteristic equation here, if you imagine in terms of the Z inverse, they have to be outside the unit circle, or in terms of the Z, they are inside the unit circle. So, for example, for an ARP process, the roots of the characteristic equation, if you were to write, would be 1 plus sigma dj z to the minus j. I am just using a different dummy variable here, sort of I am using j running from 1 to p. So, this is our characteristic equation. Lambdas are the roots of the characteristic equation in terms of z. They have to be inside the unit circle, but if you think of roots in terms of z inverse, they have to be outside the unit circle. In any case, you will have p roots, all right. So, one has to be careful when one reads the conditions of stationarity in the different textbooks. And there is a proof given for stationarity, that is when this that the stationarity is guaranteed if and only if that the characteristic equation, the roots of the characteristic equation are outside or inside the unit circle accordingly, in for example the book by Shumme and Stauffer. But I feel that the proof is now obviated, it is not needed. I have already stated right from the, we have already stated from the beginning that H is of this form, and then lambdas are such that they are less than 1 in magnitude, and I will choose these such that lambdas are that condition is satisfied. The only issue is it is not as easy as it was to derive the difference equation form for AR2, AR3 and so on. For AR1 it was pretty straightforward, you just had to write Vk equations for V at k and k minus 1 and do a simple algebraic jugglery. But now for AR2 you would have to write at k, k minus 1, k minus 2, think of some kind of jugglery and then come up with your difference equation form. In fact, for the AR2 for example, what would be the relation between D1 and D2 and lambda 1 and lambda 2? In the AR1 case it was straightforward, D1 was minus lambda 1. What would be the relation? Oh, you are already given that lambdas are the roots of the characteristic equation, right? Sorry? D1 is lambda 1 plus lambda 2, is it, or minus? Okay. D2 would be is that correct? All you have to do is imagine what is the characteristic equation in terms of D1 and D2, it would be 1 plus D1 Z inverse plus D2 Z inverse square, and this you will have to write as 1 minus lambda 1 Z inverse times 1 minus lambda 2 Z inverse, sorry. Now is it clear? In fact, you should quickly verify that it specializes to AR1 when you throw away lambda 2 kind of, right. When lambda 2 is 0, it should simplify to AR1, does it? It does. So, that is a simple check. Any questions? Fine, simple quadratic stuff. So, that is a connection, that is a mapping between your lambdas and DIs, and we have converted the condition on lambdas to a condition on D. You are saying that D should be such that the characteristic equation has the roots outside or inside the unit circle and so on. Okay.